Okay, good afternoon to everybody. Welcome to the first in this webinar series where we're going to be talking about climate change impacts on renewable investments. We're just waiting for other participants to join, so we'll hold fire for a couple of minutes, and then once we've got a few more participants on, we can get started. Okay, welcome everybody to the webinar. We've just been waiting whilst a few other people join, but I think we'll get started now, otherwise we'll probably run out of time. We've got quite a few things to get through, so we'll get started. Thanks very much for joining. This is the first in a series of webinars we've got planned, but I'll give a little bit of context for that as I'm introducing everything, and I'll also give a quick introduction to the Institute for Environmental Analytics, for those that perhaps don't know the organization so well, and then we'll get into it. So to begin with, the Institute for Environmental Analytics, we're a market-facing R&D organization, and we specialize in complex modeling for organizations in the energy sector. We are specialist data scientists, software engineers, and climate modelers, and we apply those skills to develop new decision support tools and insights for our industry collaborators and our customers. So our mandate really is to be ambitious. We apply ambitious thinking, novel technologies to try and solve complex real-world challenges. And over the past few years, we've been starting to look seriously at the challenges that are faced by investment decision makers who are looking to risk assess new solar, wind, battery storage assets. We're in the process of building a weather-based energy system, and it's our understanding that weather-related variability, and perhaps even more so climate-related variability, are not as well modeled as they could be by existing methods and assessments. As the energy transition progresses, we have increasing volumes, obviously, of weather-based intermittent renewables, and we also have a shift away from government-backed subsidies and from utility-backed offtake. And so as a consequence of that, we are starting to see more acute exposure to weather-related variability and climate-related variability, and also a shift in the way in which risks are allocated. So investors and developers that historically perhaps have been shielded by government-backed subsidies and other things from having to take on some of this complexity and some of this risk, they now have an opportunity to do so if they can get comfortable with doing it, and they need additional tools for doing that. So we'll be talking about some of that in the context of this webinar. The very first one in this series of 3, it's focused on climate modeling, climate change, weather modeling, and we'll be looking at the implications for resource, the solar and wind farms, and how that might look in the future. And in the second one, we'll start to move on to the implications for price formation, for capture, for revenue, And in the final one of the series planned for later this year, we'll start to look at financial modeling and risk management and how some of those things may need to evolve in order for these new data sets and new insights to be assimilated into current processes. So to start off with, just some key takeaways, things that we'd like you to take away from this webinar session, because there'll be a lot of information shared. These are some of the key things. So clearly, weather and climate-related variability, they are just two things amongst many that investment decision makers need to consider. We also realize that in all likelihood, these things on their own are perhaps not the most material concerns that people will have. They'll be worrying about cannibalization, price volatility, supply chains, connection queues, and we could add geopolitical uncertainty to that list as well. Those will be high priorities. But as I've said, as the energy transition progresses, we'll see more intermittent renewables in the mix, and current methods will become increasingly less fit for purpose. Why? Because what they are effectively doing is relying on averages. And with that comes the increased risk of missing potentially material upside opportunities and also potentially material downside exposures. So what we're looking for here is an ability to be able to properly integrate weather and climate-related variability into market modeling, not because it is the most material thing to be concerned about, but because if we are able to do that, we'll then be able to mitigate more effectively the key considerations like those things I've mentioned, cannibalization, curtailment, price volatility, and in the process, potentially unlock a cheaper cost of capital. So with those things in mind, we'd like to launch the first of two polls to see where the audience is at in terms of their current methodology for accounting for weather and climate-related variability. So you should be able to see that on your screens now. The question is, how are you currently accounting for weather and climate-related variability in your investment decision-making? So some options there. If everybody can make a selection, we'll give a couple of minutes for those to come through, and then we'll see what sort of distribution we have in terms of those on the call. So a couple more seconds just for some answers. I can see some answers coming through on those options. And then we'll have a look at the results. Already quite an interesting distribution. All right, so we'll end the poll there and just show you those results. So quite a lot of people, the majority, not taking weather and climate-related variability into consideration at all, which is interesting. And a couple of people already using multi-year historical time series, which I guess is what we would have expected. What we might have expected as well to see is some people using typical meteorological years and sampling from historical years. So we'll bear that in mind. We'll move on through the rest of the webinar, and I'll now be handing over to my colleague, Alan Yates. He's the Head of Energy Applications here at the IEA, and he will be talking us through the rest of the presentation till we get to the end. We'll wrap things up again. Thanks, Alan.
Hello, everybody. I'm going to take you through some work that we've done, a very quick sample study that we've done looking at climate futures. In order to do that, I think I have to introduce, firstly, especially given the results of that poll there, some of the issues around what is a weather model, what is a climate model, what are we looking for when we're modeling energy systems, and some of the practicalities around that. Define a bit of terminology, because there's quite a lot of terminology and acronyms in the climate world, and then move on to this very quick analytical study we've done comparing a couple of climate modeled timeframes and seeing what the differences look like between them. And that will highlight a whole series of issues that are very relevant to the whole question of what is the impact of climate on our modeling, on our portfolios, on the energy generation of the future. I think the best way to do this in terms of questions is to drop things into the chat as and when you can. If you have them, I'll take questions at various points throughout the presentation, especially towards the end, and Andrew will sort of feed those back to me, and we'll try and keep tab on who's doing what and who's got which question as we go. So what do we mean by a weather model? What do we mean by a climate model? Weather modeling and climate modeling, it can sound pretty similar in many ways. In fact, a lot of techniques are quite similar at a physical level, but the goals and the methods do differ slightly. From the point of view of a weather model, we're trying to predict the state of the atmosphere over a short period into the future, typically a few days. And it's quite typical that our predictions become quite a lot less reliable the further out we go into the future, as we go through days into the future. And the data that's available to us as energy modelers comes at a certain resolution. For a regional model, we might have 3 kilometer resolution on weather parameters and time steps of 10 minutes to an hour. If we compare that with climate models, the objective is to try and predict long-term changes in the distribution of the weather. So that gets reported more as changes in averages, averages of the atmospheric state, extending century, 1 century, or even multiple centuries up into the future. In some ways, it can be that climate predictions might be more predictable. We might be more certain and more confident, for example, that average temperatures will rise by 2 degrees, even when we can't predict the weather in 3 weeks' time with a lot of confidence. But nonetheless, uncertainties still exist, especially in the extremes, and we'll see some of the variability that there is in climate model outputs in the course of this presentation. And the resolutions in terms of time and space are broader, they're wider, they're larger. So our time steps only go down to hourly at most, and can be more typically daily, and the spatial resolutions are wider as well. So this gives us some issues, as we shall see. So climate models set the future context, but to model an energy system, especially one with high degrees of intermittence in it, we need high resolution weather assumptions. So in fact, we really need to extract weather cases out of the climate models and then test those against our energy system. Why do we need high resolution data? Well, for some of you, I'm sure this won't be news, but just to highlight the point, there are a lot of non-linearities in energy system modeling. So as modelers, we tend to like linear relationships because they're simple, they're easy to compute, and they're easy to validate. So if an input changes by a certain amount, the outputs change by some simple proportion of that amount. That's what we mean by linear change. But there are many non-linearities in energy system modeling. So for example, here, you're looking at a power curve. And if our wind speeds in this, can I get my pointer going here? If we have wind speeds ranging in the range of 7 to 12.5 meters per second, we're on the ramping part of the power curve here. So our power output will have a distribution based on that ramp. It has a particular characteristic shape. But if our wind speeds are fluctuating along the flat part of the power output curve, we'll have a totally flat output. And if our wind speeds are varying on and around the cutout, we have this typical cutout in a wind turbine. Wind speeds above that level will involve in a cutout of the wind turbine, and therefore output drops to 0. So we would have a fluctuating bimodal 2-mode output with frequent jumps between one level or between 0 and the maximum. Maybe smoothed out a bit by having hundreds of wind turbines in our wind farm. But fundamentally, you can see we've got different types of distributions associated with different parts of the wind speed spectrum. And solar response is also nonlinear. So we have the typical solar curve as the sun rises and falls through the day. So if what our climate model is outputting is a daily average, that's not really very helpful to us in terms of understanding that diurnal profile. And also the efficiency of our solar panels varies with temperature. So the hotter it gets, the less efficient they become. So these are non-linearities as well. And then on top of that, as we put more intermittence into our system, we get correlations that are driven by the weather. And there are time correlations within that weather. So depending on where you are in the world, there will be different weather regimes. And this particular graphic that you're looking at here is from a project that we'll probably highlight in another webinar to come. But it was looking at the effect of weather systems on system prices, electricity system prices, when we have large proportions of renewable in the mix. And it was applying historic weather conditions to different future energy system scenarios. And we were picking out of this, for example, a period of time in the past, in 2006, when there was an anticyclone sitting on top of the United Kingdom. Anticyclones in winter generate very cold weather. There'll be no wind. It might be a bit gloomy. This is your classic Dunkelflaute, as it's called. But these are very stable conditions. They don't necessarily happen very frequently, but when they do, they stick around. In this particular case, it stuck around for about 7 to 10 days. And in our stylized, we had a least cost dispatch model, modeling a future energy system in the UK. This would give rise to a sustained period of high prices over a long period. But more typically over the UK, we get cyclones that pass over from the Atlantic. And there was another period historically in 2020 when we had a sequence of several storms which passed over the UK. Storms cross the UK over a period of 3 to 5 days, typically. In winter, they'll be associated with high wind speeds, but relatively high temperatures. And if we've got lots of wind generation, lots of offshore generation in our system, we'll get lots of generation from that, and that would drive prices down typically. But the length of time with which those conditions would persist is going to be different. So there are these complex spatial and temporal correlations that we have to take into account in our energy system modeling. So in summary, we need high frequency of observational or modeled data to base our system modeling on, high spatial resolution as much as possible to resolve the different topographic effects, especially if we have a portfolio with many installations in different regions. We want to capture these internal correlations that there are in the weather, especially if we have our portfolio. Those requirements are generally well satisfied by present day what are called reanalysis data sets. If you're not familiar with that term, the reanalysis data set it's the best view that we have of historic weather, taking into account all the information that is now available. And those of you that do energy modeling will be familiar with things like ERA 5. ERA 5 is a classic and frequently used reanalysis data set, and it is designed to meet all these requirements. But climate model outputs are typically stored as averages, and a lot of this time varying and spatially varying information is lost. And as we'll see, some processes like cloud formations don't necessarily resolve very well in those models. So the climate models don't necessarily meet all the ideal requirements that we would have for our energy system modeling. So I'm going to go on now and talk about the climate models themselves. Another big difference for climate models is we have to make some assumptions about the state of the Earth system in future. And we can define that by a number of criteria. What's changing, and specifically greenhouse gases. Obviously, CO2 is the most important one, but there are others that are also relevant. Where the changes are occurring is relevant. If you look in this chart on the top right here, you'll see red areas and green areas. The red areas are very high emission areas, and the green areas are sort of lower emission areas, but nonetheless, those are where they are being detected. And if your climate model is going to be any good, you have to make sure that you get the spatial distribution of those impacts right or credible, because basically your model won't work very well if they don't. We also have to make assumptions on when the changes are occurring. And in the climate modeling community, a number of standard scenarios have been created to try and work out what are feasible potential futures for the future. And there's two bits of terminology I'll introduce here because it's relevant to these scenarios. We have RCPs, or representative concentration pathways, and SSPs, shared socio-economic pathways. So the RCPs represent potential future trajectories for greenhouse gases. For example, this plot down here is showing you for CO2. You'll see some dotted lines going left to the right across the bottom, which are different RCP assumptions about what the concentration of CO2 is going to be in the atmosphere going forward. For your reference, in the example I'm going to talk about, we're basing this analysis on RCP 8.5, which is this line up here, which is, I think, the most extreme scenario, or one of the most extreme scenarios. It's a useful one to study because extreme scenarios will have clearer signals amongst the noise, if you like. So if things are happening, they'll be easier and clearer to see from that point of view. But also, we are pretty much on that trajectory anyway, so we'd better make sure we understand it. So the climate modeling community gets together and makes, oh, sorry, I realize I've forgotten, the socio-economic pathways, SSPs. These are assumptions about humans and their effects on the Earth system. So how many of us are there? How much energy do we consume per capita? What's our relative prosperity or ability to uptake new technologies? These are the socio-economic pathways. So those are the SSPs. So the climate modeling community has created these standard scenarios. You can think of them against these two axes. So in this particular diagram here, along the bottom, you've got the different SSP assumptions, ranging from a sustainable view of the future through to fossil fuel development. And then you also have RCPs on the y-axis here, if you like, rolling up from RCP 2.6 to RCP 8.5. Out of all the different combinations, there are some that are regarded as more priority scenarios to calculate, either because they're either more likely or more indicative. And again, I'll just mark your card and say we're focused on the 8.5 scenario up here in the analysis that we're looking at in a minute. But just to highlight that there are these alternative views of the future that need to be considered. So how do the climate models work in themselves? Similarly to weather models, we divide the planet's atmosphere into a three-dimensional grid and also the Earth's surface into a grid. And then basically we apply some physics to each of these grid cells that we can see on the chart here. So basically differential equations based on physics, fluid motion, things like conservation of mass, energy, fluid dynamics. You put all those things together and then you calculate the resulting weather variables from that and other essential climate variables as well. And this is done, can be done globally. So there are many global models that are available that will cover the whole globe over long time frames into the future. So that's a global model. Just to give you a sense of how the spatial resolution of climate models is improving, this is slightly out of date now, but from 1990 through to 2007, this shows you the increasing resolution of those grid cells. We're looking at, let's say, Europe. We can see 1990 Europe is not particularly well defined. By the time we get around to 2007, you can see Europe being much better defined, and therefore the topography and the relief effects will be much better represented in our model. And this is out of date now. In fact, I think this is 100-kilometer resolution. We're now down to 50 and probably increasing by now. So the model resolutions are improving. It does imply a lot of data to process and quite a lot of processing, but things are getting better. There are still some things that are a significant challenge, and if we're concerned about solar production and clouds, then there are particularly issues around that. So the microphysics of clouds occur at very, very small spatial scales, really tiny compared with those grid cells. And therefore, to sort of fill in that part of the jigsaw, the modelers will use a technique called parameterization. So that's basically adding equations that fill in that gap based on constants, which sometimes are, in the jargon, not well constrained. And not well constrained means there's limited information really to validate them, or maybe limited theory to validate them. So there's got to be some uncertainty around the values of the inputs that we're putting into those parameterizations. So that's something to bear in mind, both weather and climate, and we'll see some of these issues later on. So I've mentioned the global circulation models, the whole globe, long time frames into the future. Because the global models don't give us as much resolution as we'd like, we will have some regional climate models that are nested within it. So the global model is run, produces some boundary conditions, which is then fed into a more detailed regional model. And again, there will be multiple versions of that depending on where you are in the world. So we can nest multiple regional models within a single global model. And here are 14 of the better known ones. There is a question over which do you choose and why. And equally, there are multiple potentially regional models driven off by these. So we do have an issue over how to choose them. What I'm going to do here is just set the scene for the example that I'm going to talk through in a minute and say out of many, many different options, we narrowed it down to 2 options that we wanted to look at to do a comparison of a portfolio. So option A here is taken from a regional model, JERICS REAM 2015. We don't need to worry too much about what that means. Based on a particular global circulation model called IPSL. So you'll see in some of the future slides, we refer to IPSL. It's just a shorthand for this option A here, produced by this German project, which had a focus on Europe, a spatial resolution of 12 by 6 kilometers, and with variables output at an hourly resolution for temperature, wind speed, and irradiance. So that's all good. But we do have an option B in the UK, which is something that we can call UK CPN 18, UK CP 18, CPM. Again, I'm not going to unravel that acronym really, but this is a model created by the UK Met Office, driven by the Hadley Centre's global circulation model. This has a particular focus on the UK and has a higher spatial resolution. So a resolution of 2.2 kilometers in its grid squares. It's a convection permitting model. Now that's a term that in climate modeling means it basically models convection better. So it models the travel of parcels of air through the atmosphere in a more resolved fashion, and therefore it's better at picking out intense small storm events and things like that. So in general, we want it to be convection permitting, so that's a good thing. And then our variables of interest, if we're modeling wind and solar, temperature, yes, we have that at hourly resolution. Wind speed, yes, we do. Irradiance, no, we don't. We can't get irradiance out of this model at the time at the hourly level. It is available daily. It was probably calculated at the hourly level along its processing chain, but that's not been stored and is not published for us to be able to get access to. So those non-linearities that we're talking about associated with solar, we're stuck on that for option B at the moment. So that's a shame, because ideally we would probably prefer to use, if we were studying in the UK, which is where this example is based, we would prefer option B, but we can't use it. We're going to have to go with option A instead. So I'm just giving you that as an example of the sort of issues that you have. You have to go out, choose from quite a wide variety of options, the models that are available and what you want to use. But then you find as you drill into it that some ones just get ruled out on the basis of what you can physically get your access to. Also, actually acquiring the data is a challenge because of these large data formats, that the large data volumes being processed, the formats can be a bit tricky to handle, and it can be a bit of a fight to get your hands on them. But that's okay. That's why we're here. That's the sort of work that we do. But these are some of the issues that you have to tackle if you're going to try and quantify these climate change effects. So, with that as a starting point and an introduction for you, I'm going to go now into just a very quick exercise that we did to try and say, well, what would happen if we compared a portfolio in 2 time frames? What does one of these models tell us about what's changing? So to do this, we used a tool that we have for modeling portfolios, which is called Energymetric. More on that on another occasion, really, but it's just a tool that we can use to say we will select different weather data sources, we call them weather data products, and drop portfolios on the map and model the production that we get from them. So in this case, here is Energymetric set up with that's the Jerix option A that I was referring to earlier, based on the RCP 8.5 portfolio. We've selected that. We've had to go through the process of acquisition, and now we can set up a portfolio for this region that's shown on the map, because that's what we've selected and acquired the data for. So we've created a purely hypothetical portfolio, basically 18 offshore wind farms, 18 onshore wind farms, and 18 solar PV plants, all with an identical specification. So there's no science in trying to match the specification of the wind turbine to the location or anything like that. We've just put an identical specification in each of these marked points for offshore, onshore, and some solar, all with an 80 megawatt capacity. And then what in Energymetric we can do is we can then run that portfolio against a selected weather data, set of weather data, in this case, this IPSL climate modeled future. Before we did that, we did compare the IPSL data historically. So the climate models will run from over a historical time period so that they can be calibrated against today's against historic weather data before they're run into the future. So we first checked that out to make sure that that was looking good, and it was. And then what we've done is compared 10 years, a 10-year time frame, 1986 through to 1995, and we've compared the same portfolio in a period 2026 to 2035. So a 10-year period, so that we get a bit of variability and variation in the weather data, but 2 distinct timeframes, 86-95 compared with 26-35. If we just look at the wind production then, so not the wind speed, but the actual production from all those offshore and onshore sites, we can model it at different exceedance probabilities. So EP is our shorthand for exceedance probability. This is the 90% exceedance probability production value, or 10% on the right-hand side. And then if we look at the color scheme, red is indicating that the wind production is going to go up according to the IPSL model, and blues and greens are indicating that it's going to go down. So we can see some regional spatial variation here. We can see the model is thinking that North Sea production is going up. Onshore, it's a bit more of a mixed case, and it varies very spatially as well. If we look at the change in the distribution of those power outputs. We can see that there is a shift. So the way to interpret this chart here is if you see orange, that implies that the frequency of power at that level is increasing. So we're seeing around about 1250 and upwards as an hourly power output. The frequency of occurrence of that is heading upwards, compensated for by a reduction in the frequency with which we're getting powers further down the scale here. So if you're seeing cyan, that's implying that there is a reduction in the frequency by the time we get to 2635 when compared with 8695. So a shift in that particular distribution. And we can look at those shifts in another way. We can look at each of these locations, which we've given a nominal name on the map here, just so we can, for ease of reference, really. If we compare the capacity factor that we get on average over the first 10-year period with the second 10-year period, the first 10-year period, 86 to 95, is shown in blue here. And then the red square is the 2635 equivalent. So this is exactly the same specification of wind turbine, but operating under the climate modeled future weather. And we can see for the offshore wind a sort of distinct pattern of slightly increasing capacity factors and decreasing standard deviation. So the y-axis on this plot is giving you basically the standard deviation. So the variability of the hourly capacity factor on the y-axis versus the average hourly capacity factor along the bottom. So if you're going right, your capacity factor is going up. If you're going up, your variability is getting more. If you're coming down, the variability is getting less. So we can see there's a definite trend, according to the IPSL model here, of a reduction in variability. If we look at the same plot, but for the onshore wind, it's a bit more of a mixed picture there. It has a different shape in terms of its positioning on this plot here, but much less of a distinct trend. Some increases in variability, some decreases. I can see a general shift to the right in terms of the red squares, but not as pronounced as in the offshore case. And if we look at solar production, and if we compare the power production that we're getting from solar, identical specification operating under the new weather decade, if we call it that, we're seeing consistently, according to this model, a decrease in solar production of a few percent, typically. And again, if we look at that distribution, so we're getting an increased amount of lower power outputs as an hourly power output, and a slight increase in the higher, sorry, a decrease in the higher ones and an increase in the lower ones as we move forward into the future. And our capacity factors in this case, according to the model, have a distinct trend. The trend being downwards. So we're moving to the left on this plot with less capacity factors, downwards as well, meaning less variable. This plot is just showing you all those three cases all plotted on the same chart. So we can see the distinct regimes that occur for offshore, onshore, and for the solar. But what we've added to it is the portfolios. So this is, if these were all totaled together as a portfolio, what would be the net effect of all of them together, which is something we can do in Energymetric. So we can see here that, we're getting the average of the capacity factor compared with the group. Let's say we're talking about offshore wind, we get an average capacity factor, but with significantly reduced standard deviation in general, and that you would expect because of the diversification effect of having a portfolio. So we see some changes according to this climate model. What's driving those changes? Well, let's look back at the weather. Can we identify the patterns in the weather which are driving those changes in production? And are they consistent? Would be another significant question. If we look at different climate models, do they all say the same thing? If we look at the projections of wind speed, this is from the IPSL model. So just to remind you, that was option A in that option selection. What we're looking at here is the relative changes in wind speed at 10 meters for the different seasons. So on the left, we have the meteorological winter, then spring, then summer, and then autumn on the right-hand side. And the color coding is giving you the percentage change. I think it's percentage change, is it? And we can see that there is a definite spatial pattern here, and the patterns are not the same. So there's definitely some variation amongst the seasons. And according to this model, some parts of the region will be having moderate increases, others will be having significant decreases. So according to this model, up in the west of Norway here, we've got some significant decreases in wind, but it's not the same picture in each particular season. So there's definitely some spatial and temporal variation going on here. And the same question arises, or the same characteristics arise if we look at irradiance. So our irradiance changes vary both spatially, depending on where you are on the map, and between seasons. But in this case, we can see a fair amount of grey, especially in spring, indicating decreasing irradiance, for example. But again, spatial variability and temporal variability as well, just within one climate model. So if you remember, if we go back to my option choice between option A and option B, it's not possible for us to make these comparisons at an hourly level because we haven't got the irradiance data from our UK CP18 model. But we can compare mean values and we can compare daily averages as well. So let's have a look and compare with the daily projection of wind speed, daily average projections of wind speeds between the IPSL model and the UK PC18 model. Same color scheme, again divided by season. This is just what you saw before. The top row is what you saw before in the IPSL slide. But here we see UK CP18's view of the world, and that's quite significantly different. So this is highlighting to you a characteristic of looking at climate models is they are not going to give you the same view of the world necessarily, or how the world is going to be necessarily. And we might see some quite distinct differences. If we look at the irradiance, there are most definitely some distinct differences, and especially if you look at CP18, that is basically indicating a much higher irradiance going forward into the future. But if you remember, our model was something that was called convection permitting. So one of the good things about having a convection permitting model like UK CP18 is that it resolves convection processes within the atmosphere very well. It's much better for identifying storms, events, and things like that, which is a good thing, but it comes at a cost. And we think the cost in this case is that it tends to be a bit optimistic about irradiance. So another feature here of climate models, they have to focus on particular issues. They can't all get all things right all at the same time. So what's the solution? Or actually, the solution is probably we need to look at an ensemble of models. And we've taken this from a paper that's just been recently published by Olivares Carvalho, doing something somewhat similar. basically taking a standard specification of wind farm and comparing two locations, actually three locations, but we're only showing two here, and running each of these 14 or so CMIP6 models against them and seeing how would that compare with the current ERA 5 calculation for multiple financial parameters, but in this case, we're just looking at the IRR, internal rate of return, based on a particular specification. And what you see for these different shared socioeconomic pathways, so we've got some different socioeconomic assumptions going forwards. You can choose which one you prefer, or take a view on which one you prefer, but the dots in the diagram is showing you different models showing different differences of IRR, and these are box plots. So the squares here tell you that 25%, the 25 to 75%, what's called the interquartile range of models, is giving you values within the shape of the box. So outliers are sitting above and below the boxes where the majority of the different climate models are agreeing. So you can see quite a lot of difference. Again, the big message: spatial variability, temporal variability. But at least you can see here what the likely expected maximum variability might be. And so that's giving you something that you might want to feed into your financial analyses when you're doing your sensitivity analysis. I mentioned this before, time correlations are a feature of the weather. They affect system prices. This is a little teaser for another webinar that we're planning to put on, where we look at different categories of weather. So we categorize weather types and we look at them in terms of their impacts on system prices and the characteristics they have on system prices. You'll remember I highlighted that the high pressure systems move quite slowly. The storms pass quite quickly, and we can have these different regimes where there are successive days with similar weather characteristics and also similar system price characteristics. If we look at that, this is an extract from this other study that we've done where we looked at comparing. This was a CP18 model, but it was actually comparing to 30-year timeframes centered around 2022 and 2030. And we were looking at how long particular weather conditions would persist. So if we think that as a run length, so a run length might be high prices persisting for a particular number of hours. And the distribution of those run lengths is changing. Basically, we're getting an increase in run lengths as the system evolves from 22 through to 2030. But if we focus in on the tail, so the tail here being from 200 up to 700, and if we zoom into that and bump it up, we get the chart on the right-hand side here. We can see that in the tail, in extreme events, the opposite is happening. There is a reduction in the far extreme of the tail, whereas in general, the high price run lengths are increasing. Very, very long tails are showing up as a decrease. So discuss, is that significant? If you're concerned about activity in the tails and extreme events, that may be something that's worth further discussion. So there we go. In summary, there are some hard constraints on the weather data that we need to model our energy systems. There is a certain amount of complex data handling and wrangling to get the data out of these climate models. I've shown you what results might look like from a very quick investigation into a single model. We've seen that the models do show some statistically significant changes, but there is variability. There is variability between those climate models, and therefore probably the solution to that is to have take an ensemble approach, look at as many of the models as we can and take an ensemble view if we want to get a credible assessment. I think that's it from me.
Okay. Thank you, Alan. Right, so we've got one other poll that I think we wanted to try and use just to finish things off, and then we'll have a look at the questions that have come through on the Q&A. We've also got a couple of questions which have come through from others that couldn't attend today, but which have nevertheless asked some questions, which we will also try and go through. So before we do that, just to recap on those key takeaways. So what Alan's done is gone through the first in this series of webinars. We've been trying to introduce to you here the practicalities and the challenges of working with weather data and climate data, and what it all means for the potential of future solar and wind resource, and then, of course, the implications for associated production. But the direction of travel here is not just, this is the starting point. The direction of travel is to try and understand how we can then start to integrate properly weather variability and climate variability into the things which people really are interested in, which is the implications for price formation, the implications for capture, and then the implications for revenue. So that will be the focus for the next webinar, which we'll be setting up hopefully in the next few weeks, perhaps a month or so from today. We'll let everybody know when that's going to be taking place. But just to wrap things up on this particular one, I'm going to launch the last of the polls, which we're just really interested in people's views on whether this session itself was helpful. So just interested in people's views on whether they've learned some things today, whether there were lots of new things in here, whether there were just a few things which were new, or whether others already knew all of what we have been talking about. So if we can just get a selection on those, that would be very helpful. We'll just give a couple of minutes while those responses come in, and then I'll share the results with that one as well. Okay, so thanks very much to all those people that have responded. Quite satisfying from our perspective. If I share those results, seems that most of the people on the call have learned something useful from this. So that's good. We've started in the right place. We're pitching at the right level, and we'll be taking all of this forward into the next sessions. So I'm just going to have a quick look at the Q&A now to see if there's anything in there. And if there aren't, if you've got questions, please feel free to type them into the Q&A chat. We can still deal with those now. But just to kick things off, we've got a question which we quite regularly get asked, and which people are generally quite interested in, where this climate change, weather variability, the implications for renewable investments is concerned, particularly around wind. And the question is around global wind stilling, and to what extent this is happening, to what extent this is a concern. If you're a wind developer, should you be worried about wind stilling? So I'll hand over to Alan just to say a few words on wind stilling.
Yes, you will hear the term being used, and it's mentioned in news reports and things from time to time, and in academic studies. I think the basic principle is, certainly in terms of the UK, the circulation over the UK is driven by the temperature and pressure differences between the poles and the equatorial regions. And with climate change, there will be there's an expectation that the poles will warm, and that circulation, the driver behind that particular circulation, will be dropping slightly. I think if you think back to those charts that I was showing, one of our basic messages is, I mean, averages are dangerous to use in terms of certainly in terms of your financial evaluations. And what we could see from those charts, even within one model or between both models, and probably if we looked at more models, is that there's quite a lot of variability between region. So it may well be true that there is an average stilling effect, but the effect for you in a particular region or with a particular portfolio might not be subject to that. But it's certainly it's an area of investigation that we would certainly be interested to delve into.
Okay, thanks, Alan. And one other topic that we get asked about, I guess, when people are starting to become more aware of these sorts of risks, and whether or not they should start thinking about how they evolve their current decision-making processes, or indeed if they even have to, is we talked about a particular driver here being the energy transition, right? So there are more renewable, variable, weather-driven solar and wind resources in the generation mix. That's driving complexity in the markets. That is the reason why you would want to start looking at things in more detail, and you may want to shift some of your current investment decision-making process. But at what point does something like this become relevant, right? So if there is an energy transition happening, what kind of level of penetration of renewables is required before some of these things start to become a problem?
Well, I think it depends where you are. You know, if your level of penetration is down, if you're in a region or on a system where your penetration is just a few percent, it's really not a significant effect. But certainly in the UK, I think now we're beyond that. And if you're talking about 20, 30, 40, 50% penetrations of renewables, it most definitely is already significant and is likely to become increasingly so as the penetration goes up. So we keep referring to this, but we have another webinar hopefully coming in the future where we will try to highlight some of the significant effects of increasing percentages of renewables and how the impact of weather changes as they go up. So I don't want to steal that thunder too much.
Okay, and just maybe one final question, just to wrap things up. We've just got a little bit of time for one final question. So the obvious observation from all of this is that there's a lot of complexity when looking at climate data. There's lots of different climate models. There are lots of different ambiguities potentially and uncertainties which emerge from dealing with all of these things. So the question is, why are there so many climate models? Is it possible to simplify this landscape a little bit to reduce these apparent ambiguities or uncertainties, or are we stuck with all of this for now?
Well, I think in terms of why do we have so many, although there are global models, every global model has to have a focus, and typically there will be some sort of regional focus, and therefore you try to calibrate your model to the requirements of that particular region. We have a slide that we took out that showed some of the variability and the distinction between them, but the other thing we've seen in this presentation is that by trying to be really good at one aspect, for example, trying to be good at identifying small, intense windstorms, that will come at the expense of something else. So if you're in a region or a part of the world where it's the intense windstorms that you're really concerned about because of damage or flooding or whatever, then that will be the focus and that will be the calibration. Whereas in other regions, it will be more important to get other factors right.
So no clear winners at the moment, and no obvious way in which models can be weighted, which would allow for the exclusion of some things and the inclusion of others. So to begin, for now, we are going to have to deal with this complexity and find ways to navigate that and still extract useful insights from it. So I think at that stage, we've finished the time we have allocated for this webinar. So I'd just like to say thank you very much to everybody who's joined. This is the scene setting webinar really, in a series of 3. The next one will be focused on price formation, capture, revenue, and how all of this uncertainty plays into those kinds of questions. And then the final one in the series, we'll start to look at financial modeling, risk management, and how some of those processes may need to evolve if we're trying to assimilate some of the things which come out of the type of work that we are doing. So hopefully you'll be able to join us for that one in the next series. Look out for the communications via LinkedIn or other channels for that, and hope to see you again on that webinar as well. Thank you very much for joining today, and goodbye.